Hey everyone! This lesson is going to be on converting between rectangular and polar coordinates and equations. So this lesson assumes that you already understand the basics of how to graph a polar coordinate and what it is. In case you need a quick refresher, remember polar coordinates still work on a coordinate pair, but now instead of having an x-axis and a y-axis, we measure things based in the radius or the distance from the origin or the pole and in theta. And theta is the distance of rotation around the circle that we're following. Now, it's important for you to realize when we're using the polar coordinate system, it still aligns with the unit circle that you've used in previous lessons. So you're going to have to keep a copy of your unit circle nearby so that you can reference it. So for example here, this line would be an angle of 30 degrees or pi over 6. This one would be 45 degrees or 4 pi over 4. On and on. So as we're working today on converting between rectangular and polar, you're going to need to have your unit circle handy because we're going to be working with cosine and sine, which align with the x and y coordinates on the unit circle. So don't think that just because we're on a new unit, what we learned in the last one has gone away. It's still going to be very important that we use those skills. So the first thing we need to realize is that a point for polar coordinates technically has an infinite amount of points. The reason being, if I were to choose a point here, and I choose the point 2 and 45, get my pen working. That's 1 point, so 2, 45 degrees. And we can write polar coordinates in either degrees or radians, depending on what the problem is. So this means I went out to 2, and then I rotated 45 degrees. But what I could have is I could have a whole nother revolution. So instead of going around once, we could have a revolution where it went around twice or 3 times. So what this formula here says is that we could have our radius, and then it could be theta plus 2 pi, and remember 2 pi is an entire rotation, times n, where n is any integer. So if I rewrite that over here, r, theta plus 2n pi, I could write another for an infinite amount as 2, 45 plus 2n pi. And that represents any amount of rotations around my polar coordinate. Now we could also write it going in reverse, because remember, we always go counterclockwise, but if we were to write it as -2, now we're going clockwise, and for now we do theta plus parentheses 2n plus 1 pi. So theta, which we know theta in this case was 45, plus parentheses 2n plus 1, close parentheses, and then we put pi at the end. So those are the 2 ways that I could mark this same point using an infinite amount of points. So if we try it again, we want to find all the polar coordinates for P. So that they tell us, we look, they went over 3, and then it rotated up to pi over 3. So if I want to write that for an infinite amount of points, our two ways is we start with our r, so 3, comma, our theta, which is pi over 3, plus 2n pi, and sorry, my n's and my pi's keep getting confused. That's if we're going to go the traditional clock or counterclockwise. And if we want to go clockwise, it becomes -3. So we're starting over here. And now we're going to rotate by pi over 3 plus parentheses 2n plus 1 pi. Now I know you think that you need some sort of number for n, but in this case you don't, because n stands for the number of rotations that you're making. And we don't know until someone actually goes to do it. So those are your two answers, and you can leave them alone. So that's for if we want to list all the polar coordinates for a point P. But let's get into the more challenging stuff. We want to be able to convert from rectangular to polar, or from polar coordinates to rectangular. So luckily, there's a couple of rules that we can use that will help make life easier. When we're going from rectangular to polar, we're going to be using these two equations. The first one is what's going to give you your r value. And the second equation is what's going to give you your theta. Now, you'll notice that this looks very similar to the Pythagorean theorem. That's because it is. If you think of us having a coordinate like 2, 3, if I looked at that on our traditional rectangular coordinate, that's up there. And then if I wanted to find the radius, we can make our right triangle, pretending that's a triangle. And now we know it's a triangle with a base of 2, a height of 3, and we can do our Pythagorean theorem to find the radius. So that's what we'll do to find our radius, is do the Pythagorean theorem. Then, to find the tangent, or to find theta, we'll use the rule tangent theta equals y over x. We'll put y over x and then use our inverse tangent to find what theta actually is. Now, on the other side, if I'm starting with polar equations and I want to switch to rectangular, we're going to use these two equations to get our traditional x and y. In this case, x is going to be equal to r cosine theta, and y will be equal to r sine of theta. And we'll see how to use these in a minute. Now, when we get to converting polar to rectangular equations and reverse, your previous identities that you learned in the last unit are also going to come back. There may be times where you need the Pythagorean identities, reciprocal identities, or the double angle identities, just to name a few. So these ones we'll come back to when we start using equations. But let's go ahead and start looking first by doing polar to rectangular coordinates. So here's our first polar coordinate. It's 3, 5 pi over 6. So I know that if this was being rotated, it started with a radius of 3, and it rotated all the way over to 5 pi over 6. So my point is over here. And I want to know what that would be on the rectangular system. So we're going to go ahead, and I put our equations down here again. We're going to go ahead and just plug things in. So I have x equals r cosine theta, and y equals r sine of theta. So we know that the r is 3. So I'm going to put x equals 3 cosine, And I know theta here is 5 pi over 6. Now this is where your unit circle comes in handy, because I want to know what cosine of 5 pi over 6 is. So if I look on my unit circle and I find 5 pi over 6, I see that the cosine is equal to negative root 3 over 2. So that means I can go ahead and multiply these, and I get x equals negative 3 root 3 over 2. Now, I look at my y value, and we're just going to plug in the same info. Y equals r, which was 3, sine 5 pi over 6. Again, looking at my unit circle, I can see that 5 pi over 6 gives us a sine of 1/2. So that becomes y equals 3 times 1/2, which gives us a y value of 3/2. So our answer is negative 3 root 3 over 2 and 3 over 2. And if you don't have a copy of a unit circle handy, I will attach a document or a link to a document on my website with this video for you to download and hopefully print. Because honestly, the unit circle I've never memorized. I always have my handy paper copy and one on my computer that I can always refer to. So definitely get one of those to make your life easier on these problems. So let's try it again over here on B. So B is telling me, giving us a visual, that it went out 4 units, and now it rotated to 3 pi over 4. And 3 pi over 4 is over here again. That's technically equivalent to 135 degrees if you wanted to know. So it's over here in your second quadrant. So we're just going to use our rules again. X equals r cosine theta, and y equals r sine of theta. So starting with our x, we do x equals 4 cosine 3 pi over 4. So x equals 4 times, and sorry, my 4 a lot of times when I write, my board turns it into a 9. And I look on my unit circle for 3 pi over 4, and that gives me a cosine of negative root 2 over 2. So now I have x equals negative 4 root 2 over 2, which can be simplified into just negative 2 root 2. So now we know our x, so let's go ahead and substitute for our y. Y equals 4 sine 3 pi over 4. So that gives us y equals 4 times, we look, the sign for 3 pi over 4 is a positive root 2 over 2. So that gives us y equals a simplified 2 root 2. So our final answer is negative 2 root 2 and 2 root 2. If you need help reading your unit circle to get from this stage to this stage, let me know and I can do a lesson with you helping you to read the unit circle again. So now let's go ahead and practice converting from rectangular to polar coordinates. So now we're going to go the other direction. So just like before, I'm going to draw a visual so I can kind of see what I'm looking at. So my original point is at negative 1, 1. And I know I need to find two things. I need to find my radius and I need to find my angle of rotation. How much did it rotate from the radius to my quadrant over there? So first thing we're going to do is find our radius, because remember, this is basically making a right triangle with a base of 1 and a height of 1. So if I do my Pythagorean theorem, that gives me r squared equals -1 squared plus 1 squared. So that gives me r squared equals 1 plus 1, r squared equals 2, or r equals the square root of 2. So all I've done is Pythagorean theorem, and now I know the first part of my equation is the square root of 2. Now I need to find my theta. So our rule for theta is tangent theta equals -1 over 1, which gives us tangent theta equals -1. Now there's two ways you can go from here, depending on if you like radian or degree mode. If you like degree mode, you can go ahead and take your calculator and go ahead and do inverse tangent and -1 and see what that gets us. So I will go to my online calculator and we will type in, or we will go to functions, inverse tangent, -1, and then we always have to make sure that our mode is in degree mode, and it tells us that our angle is -45. So we know one of our answers here is that theta equals -45. Now we could also do this in radian mode by using our unit circle again. And I know in my unit circle that tangent is negative in quadrants 2 and quadrant 4. So if I look in quadrant 2, I can see that it is negative at 3 pi over 4. So my theta is equal to 3 pi over 4. Now notice we have a difference here between the two, that this one is a -45 and this one is a positive 3 pi over 4. What we have to think about is the quadrant that this ended up in. Since this is up here in the second quadrant, that's where 3 pi over 4 is. That's not equal to -45 degrees. That, we would say, is a radius of 2, and it is 3 pi over 4 degrees, or you could say 135. Now, why I love this example is because, remember, we could also start at a -√2, and that's where we would use our -45 degrees, or it would still be 3 pi over 4. So you have to think about which quadrant am I in. And in our unit circle, this point over here in quadrant 2, when it's 3 pi over 4, that is 135 degrees as we go this way. But if I started over here in the negatives at -√2, when I go backwards, now to get to that point, I'm rotating backwards 45 degrees. So you have to be careful when you use your calculator. If it gives you a negative answer, that goes with your negative r, or your negative radius. So in this problem, we have two answers. Going the traditional counterclockwise, it's √2 or 135. Or going backwards, it's -√2 or -45. So we really have to watch out with the negatives, which one we're using in degree mode. So now let me clear some space off. That's a tiny little eraser. Let's try and make it bigger. And let's try this again. So I know if I am dealing with 2, 2, we're up here in quadrant 1. So let's go ahead and do our Pythagorean theorem to find our radius. So 2 squared plus 2 squared. So that gives us r squared equals 4 plus 4. Or we get r squared equals 8. So when we square root both sides, we end up getting r is equal to 2 root 2. So now we know our first part of the equation is that this radius length is 2 root 2. So now we have to figure out how far did it rotate. So we go ahead and do tangent theta equals y over x. So tangent theta equals y, which was 2, over x, which was 2. So we get tangent theta equals 1. So bringing back our graphing calculator, we can do the inverse tangent of 1. And now that gives us a positive 45 degrees. So I can say that when I'm in degree mode, my answer is 2 root 2, comma 45. But remember, that's if we're going counterclockwise. What if we started at negative 2 root 2 and we wanted, sorry, that's a root 2, and we wanted to go that way? Now, if this is 45, we have to do negative 2 root 2, and we do 180 minus 45, and that gives us negative 135 degrees. So again, there's 2 answers. We could start at 2 root 2 and go backwards, or sorry, go the correct way, go counterclockwise, 45 degrees to get to our point. Or we could start at negative 2 root 2, and basically we find the supplementary angle to 45 to figure out how far we go, and that's negative 135. So hopefully you're starting to understand why we have 2 answers. One is going counterclockwise, and the other is going to the negative coordinate and going clockwise. The next thing we have to look at is how to convert polar to rectangular equations. So now we don't have coordinates, we actually have an equal sign involved. So this is where we have to get creative, and you're going to start using your identities that you learned in the previous unit. So I have here that r is equal to 4 secant theta. What I'm going to do is I'm going to go ahead and divide both sides by secant theta. And that gives me r over secant theta equals 4. Well, remember when things are written like this, that's the same as saying r times 1 over secant theta equals 4. Now here's where your identities come in hand. I know, using my inverse identities, that 1 over secant theta is the same thing as cosine theta. So I can go ahead and replace this and write r cosine theta equals 4. Now hopefully this looks a little familiar to you. Remember when we converted earlier to rectangular form, we used the equation x equals r cosine theta. So if we match that up here, r cosine theta equals x, I can see that x and 4 are in the same spot. So that means this equation is x equals 4. And if I were to graph that on a traditional equation or on a traditional graph, that would give us a line at x equals 4. So don't worry if you end up getting a super small answer. That's okay. Some of these are going to give us small answers, while others are going to give us huge answers. So let's look at another one like this. Now I have r equals 2 cosecant theta. So our goal is to manipulate it again to get to some sort of identity that we can replace. So just like last time, I divided by secant. This time I'm going to divide by cosecant theta. So now I have r over cosecant theta equals 2, or r times 1 over cosecant equals 2. And using our inverse identities again, I know 1 over cosecant theta, technically, is equal to sine theta. So I can go ahead and switch the two and do r times sine theta equals 2. And now this reminds me of my formula y equals r sine theta. So when I match it up, r sine theta equals y, I can see that y is equal to 2. So in this case, if I were to graph this, it would just be a horizontal line at y equals 2. So the key to success on these is just trying to manipulate the equation and getting some form of an identity that we can then substitute for. So just a couple more problems. Now we're going to try converting from rectangular to polar equations. And our goal with these is we like to try and get our x's and our y's by themselves to use that same equation that we just used on the other page. Our x equals r cosine theta and y equals r sine of theta. So just like back here, we wanted the r sine of theta by itself to find the y. Now we want to get y's and x's together so that we can substitute to turn it into the radius and theta. So here's our equation. We have x minus 3 squared plus y minus 2 squared equals 13. So you may want to go ahead and jump right in and try throwing the r cosine theta in at first. But I wouldn't advise that since we have parentheses with a squared. What I would do first is I would go ahead and use FOIL and I would multiply these out. If we do that, we get x squared minus 6x plus 9 plus y squared minus 4x plus 4 equals 13. And then let's go ahead and group these by term. So I have x squared plus y squared. I have a minus 6x and a minus 4y. And remember, my 4's turn into 9's on this program for some reason. And then I have a plus 9 and a plus 4 equals 13. So right away I can see that equals 13. So that's going to cancel out with that. So now I have x squared plus y squared minus 6x minus 4y equals 0. Now, this still looks a little daunting, but I see our first identity in sight. Since our goal is to get r's and thetas, I see right here that I have an x squared plus y squared. That is our rule for converting our x and our y into our radius. So as soon as I see that x squared plus y squared, I can go ahead and substitute r. So that whole little chunk just became r. Now I can go ahead and say minus 6, and instead of x, I'm going to go ahead and put in r, oops, that's a squared, r cosine theta, and then minus 4r sine of theta. Now as I look at these, I can see that they all have an r in common. So I'm going to go ahead and factor out an r. So if I take out an r, that leaves r minus 6 cosine theta minus 4 sine of theta equals 0. And then remember our rules, we have to set each one of these equal to 0. So you get r equals 0, and you get our whole equation, r minus 6 cosine theta minus 4 sine theta equals to 0. Now we have two equations, but I want you to think about what they mean. If this says r equals 0, well, that's just saying that we haven't moved anywhere. So it's at the origin or the pole. So that doesn't help us. But this one actually is our converted equation, where this is equal to the original. And if you were to graph both of them, you would see that they actually do match. Both of them would be a circle, whether it's on the coordinate grid or the polar grid. So that is our final answer. Let's go ahead and try one more. Now we have x squared plus y squared equals 9. And we know our two main equations is x equals r cosine theta and y equals r sine of theta. So on this one's different than the last one because there's no parentheses. So we're just going to go ahead and put r cosine theta and put the squared around it plus r sine of theta squared equals 9. And if we go ahead and square both, we get r squared cosine squared theta plus r squared sine squared of theta equals 9. Now, just like last time, I see that we have r squared in common. So we'll use our factoring skills to factor out r squared. And that leaves us with cosine squared theta plus sine squared of theta equals 9. Now, hopefully, this looks pretty familiar to you by now. That is one of our Pythagorean identities, which tells us that sine squared theta plus cosine squared theta is equal to 1. So we are just going to go ahead and rewrite it as r squared times 1 equals 9, which is pointless since anything times 1 is itself. So we get r squared equals 9. And then we're going to go ahead and square root it, and we get r equals plus 3 or minus 3. So we are going to go ahead and we will give two answers. We'll say that r could either be a positive 3 or r could equal a negative 3. And those are our two answers. So as you see, we could get a short answer like this one, or a really long answer like this one. Either way, don't be afraid to just manipulate the equations and look for our ability to substitute r cosine theta and r sine of theta in for x and y. And then definitely keep an eye out for some of our old favorite identities that you learned in previous units. Hopefully this has helped you with this unit. Thanks for watching.